Hello everyone, my name is Hasanpour. I'm from the University of Nevada, Reno, and I've been working with Dr. Istorati and Dr. Bachel. We greatly appreciate the peers sponsorship. The participants in this project are Dr. Bachel, Dr. Istorati, myself, Dr. Scott and Dr. Zhu from the OSU, and Dr. Papachristos from the UNR. Our objectives are to understand the twofold effect of debris, including impact and damming on coastal bridges, to understand the debris-wave interaction during the tsunami's propagation and debris-wave bridge interaction and the associated laws for different debris orientations, explore and calibrate novel particle-based, coupled particle mesh-based method, and hybrid particle mesh-based method, and to decipher the role of non-structural mass and develop prescriptive load equations for debris impact load for tsunami design guidelines for coastal bridges. The big question is that why we need to consider waterborne debris. Tsunami events cause failure of many critical infrastructures, including bridges, which is important due to the significant role of these structures in emergency response following the events. Field surveys after the past major events, such as the 2011 Japan tsunamis, demonstrated the significant contribution of waterborne debris to structural failure. Debris affect the structural integrity and functionality. For example, you can see here that this is a remaining boat after the 2010 tsunamis. Here is the shipping container which got trapped below the superstructure after the Japan tsunamis, and the two bottom pictures shows that the span of the bridge is removed due to the impact of shipping container. Therefore, coastal structures, including bridges, should be capable of withstanding the loads associated with waterborne debris. To investigate the applied load on bridge deck by debris, we use the novel coupled particle-based and finite element method. SPH is a Lagrangian-based meshless technique in which the continuum of a fluid is replaced by a set of non-connected particles. This modeling approach has two key steps. The first one is kernel approximation, and the next step is the particle approximation. And here are the discretized form of equation of motion for the implemented method in LSTM, including the density, momentum, energy, and strength. To validate and check the accuracy of the coupled finite element SPH modeling technique, we conducted extensive numerical investigations. Last year, I presented the two different validations that we carried out. We selected one of the largest experimental study to date, which was conducted at the Large Bay Fulham Oregon State University by Cohen Cox. As a continuation, we just modified the developed model for that validation study and just replaced the coastal column by a bridge deck and applied same numerical setting to our model. The wave maker, flume, debris, and bridges developed based on the finite element, and the fluid were represented by the SPH particles. And the final numerical model consisted of about 1.3 million SPH particles, and using up to 80 core per analysis, the runtime for each model was about 19 hours. In this picture, you can see the details of the developed numerical model. Here is the wave maker, this is the fluid particles, and here is the floating debris, and here is the bridge superstructure. One of the fundamental questions which is necessary for the future risk assessment is it possible for a designer to predict in advance the debris motion or not? In this slide, we are observing selected snapshots for two different scenarios. The main difference between these scenarios are just the deck elevation. We can observe that the debris show complex pattern as it propagates inland and impacts the deck. For the higher deck elevation, as the debris impacts the offshore side, it moves below the deck, while for the lower deck elevation, it becomes trapped below the offshore overhang, which demonstrates the complexity of the phenomenon. In terms of the debris impact force and velocity, the main focus of the available prescriptive load equation and previous studies were just on the horizontal impact force. However, our numerical results shows that the debris has significant impact velocity along the vertical direction, which is in the range of 20% up to 27% of the horizontal impact velocity. And as you can observe here, in terms of the debris impact force, in which the horizontal impact force are presented by the black curve and the vertical impact force are presented by the blue curve for different scenarios. For example, these legends meaning that for the longitudinal debris, which means that the long axis of the debris is parallel to the wave propagation, and with deck elevation of 60 centimeters. Here is we have same orientation for the debris, different deck elevation. And we have the transverse debris orientation, which means that the long axis of the debris is perpendicular to the direction of the wave propagation. We can observe that the debris applies several vertical impact loads on the deck, which is not presented in previous studies. And one of the interesting findings is that the horizontal impact force, the maximum impact horizontal force and vertical one do not occur at the same time, which highlights the need to consider different load cases to identify the governing scenarios. For the next step, we wanted to validate our numerical technique against a three-dimensional experimental study. To this end, we selected the experimental work conducted by Shafei back in 2016. This experimental analysis conducted at the University of Auckland. This is a dam break test. Here is a dam, and they use two kinds of debris, the box and the disc. And this is the details of our numerical model. You can see here that this is the water particles. Here is the column, which is the representative for the structure. And here is the two types of debris. We applied same numerical setting to this model. The final model has about 3 million SPH particles, and the runtime increased to up to 43 hours. Here I want to show you a schematic view of the phenomena. You can see here the propagation of the bore. Here is the gate, which acts as a dam for the water behind the gate. The bore propagates, picks up the debris, and debris impacts the column. Here is the zoom-in animation of the scenario. You can see that the deck impacts the column. These snapshots, we made a comparison between some snapshots from our numerical simulation and the experimental analysis. The top figures shows the snapshots from the experimental setup, and here are numerical simulation, which reveals that these techniques can capture the debris motion and the trend of the debris motion and impact on the superstructure with good accuracy. And in terms of the free surface and fluid particle velocities, our numerical results gave good close with the experimental one. In terms of the debris velocity, acceleration, and impact force, we conducted a sensitivity analysis to determine the optimum particle size. And we selected the particle size equal to 1 centimeter for our final numerical model. In terms of the debris impact force and acceleration, the numerical results gives close match with the experimental data. For example, for the disk debris, the maximum deviation for the impact force range between 1.8 up to 5.5% from the experimental data. And in terms of the debris velocity, the maximum deviation for, let's say, the disk debris range between 1 up to 1.5%. And as the next step, we use the validated 3D numerical tank from the Shafei's experiment and apply some modifications. The first one is that we replace the column by a coastal bridge deck, which follows the dimensions of the deck used in previous large experimental analysis conducted by Dr. Strati and Dr. Wakel back in 2017. The floating debris was represented by a standard shipping container. We increased the length of the reservoir from 4.2 up to 10 meters, just to ensure that we have adequate volume of water to pick up the debris. And finally, we moved the outlet 2 meters away from the bridge to eliminate any effects of boundary condition. Again, we apply similar numerical setting to this model, and the final numerical model consisted of about 4.2 million sparse particles, and the runtime for this 3D model jumped to 110 hours using up to 80 core per analysis. Here are the parameters that we are investigating. The first one is that we consider three different bridge elevation, 20, 30, and 35 centimeters. Two different debris orientation, longitudinal and transverse one. In terms of the debris mass, we consider three different ranges for debris mass, including 9.2, 50, and 75% of the total weight of the standard shipping container. And we investigated the effects of a wide range of hydrodynamic conditions as presented here. In this slide, I want to show you two animations which shows the effect of deck elevation. All the numerical settings for these two models are similar to each other. There is just one difference, which is the deck elevation. For the animation in the left side, the deck elevation is equal to 20 centimeters, and in this animation, the elevation is equal to 30 centimeters, and you are observing the horizontal velocity of the bore as it propagates and picks up the debris. Let's watch this animation. You can see here that the bore propagates, picks up the debris. The debris impacts the offshore side of the deck and moves below the deck. However, in terms of the higher deck elevation, when the bore propagates and picks up the debris, you can see here that the debris become trapped below the offshore overhang, which clearly demonstrates the role of the deck elevation on the debris dynamic and impact on coastal structure. In terms of the applied load on bridge, in this figure, you are observing the applied horizontal force. The debris interaction with the deck is presented by the black curve, and the blue curve shows the applied load by float particles. It is obvious that depending on the deck elevation, the ratio of the maximum debris to float force range between 2.5 up to 10. And for higher deck elevation, let's say here the 30 centimeter deck elevation, the applied uplift load on the deck comes just from the debris load, which means that we do not have any interaction between the fluid and the deck for higher deck elevation. In this animation, I'm presenting the role of debris orientation and debris dynamic and motion around the deck and applied load on the deck. Again, the numerical settings are similar, and including the hydrodynamic condition and deck elevation. The main difference is that in this animation, the debris is in longitudinal phase, and here we have the transfer debris. You can observe that when the bore propagates and picks up the debris impacts the offshore side, moves below, and resurfaces as the transfer debris in case of the longitudinal debris. However, for the transfer debris, when the bore picks up the debris, it impacts the offshore side and moves above the deck. Again, this animation shows that the debris orientation plays significant role on the debris bore deck interaction. And in terms of the applied load, our preliminary data shows that the debris orientation had significant effects on the debris motion. As you saw, the debris either could move below the deck or impacts the offshore side and move above the deck. And in terms of the applied load, our results shows that the applied horizontal load on the bridge, the ratio for the longitudinal debris to the transfer debris range between about 1.5 up to 2.7, depending on the deck elevation and hydrodynamic condition. Thank you so much.
There's time for questions.
Yeah.
Is there any thing
the deck is rigid here. We are not investigating the actual damage on the deck. We are just locating determining the location of the impact.
Just curious if it's making more very flexible in the future, like the get accessing the
Anybody else? Well, in that case, thank you, speak. Thank you very much again. Well, speakers for the session. And we can thank.
Yeah, we have a few minutes before lunch. Then we will do a photograph right in this room. It's more fitting with the dim lights and all the wires hanging. So instead of outside stunning picture, let's do one right here.
I'm very excited to be moderating. Not necessarily my field, but I always love to learn. So our first talk is going to be from Professor Lavi from UNR.
The second link is this the one? No, this is not the one. No, this one. Okay, so stop share and no, I have to say the standard thing. It worked perfectly a minute ago. Okay, so. One more thing. That is because here we had one more thing. Just need to move this. Hold on another minute. And then this one, speaker only. And you can.
Are we good? Okay, thank you. Good afternoon, everyone. So this is our ongoing project for peer with the topic of deep learning-based surrogate modeling for accelerating uncertainty quantification tasks in solar structure interaction problems. And we have started this project in January, February. So I just want to share with you some of the results we have so far and what are our next steps. So what is the motivation? Here I'm showing a relatively simple solar structure interaction problems. Let's consider a buried structure. And let's say that we are just interested in transverse behavior of that structure. So it's a plane strain model, not necessarily a 3D one. And then there are some sorts of uncertainties when we want to study the behavior of that structure. For example, if we assume that this structure is going to be subjected to some plane waves, the angle of the incidence, and also the time series itself, it could be one source. In addition to that, the profile, so the small strain stiffness that we have for that soil half space is another source. And ideally, if we have nonlinearity either in the structure or soil or both of them, that could also bring some source of uncertainty to the problem. And if we have unlimited resources for doing forward simulation of this problem using direct methods. So, and if our models are highly scalable, then probably we just go and do forward simulation using multiple-based approaches, and then see how these uncertainties can project on our quantities of interest. That could be, for example, the time-dependent response of our structure or some other quantities. But what if we have a limited budget and how we can accelerate such tasks in our analysis, and especially for solar structure interaction problems that are known to be relatively complex. And it really depends how good we are in terms of modeling the domain, truncate that, or how we can bring the remote excitation to the problem. So in such a case, in order to accelerate the problem, there are kind of two approaches that we may want to consider. The first approach is the reduced order or substructure modeling approach. That what we do is, okay, we can get rid of the surrounding soil by modeling the effect using some springs and dashboards. And then we may want also to make some changes into the input motion and define that at the interface of this structure. And depending on the complexity of the accuracy of such reduced order models can change significantly. So we really need to work hard to develop these springs and also the input motion, and then hopefully use them for our UQ tasks. But the other approach could be the data-driven modeling approach, that we say that, okay, if we have a limited budget that we can do some high fidelity formal simulations, then how we can use that to define a mapping from our input parameter space over the quantity of interest we have, and then how we can use it for our UQ tasks. And here, since you're interested in time-dependent quantities of interest, I'm interested to see how the long short-term memory or LSTM networks work doing these or addressing this problem, that they are known to be relatively good in capturing or predicting a sequence of data that we have. Okay, so with this introduction, in 2019, there was a paper on using the LSTM and some version of that to do a prediction of nonlinear structural seismic response. And what they did was, if you have an input parameter, which is the earthquake signal or time series, they define some stack for that. And then for each stack that they have here, each of them, they consider an output that is 1 point on for that windowing that they have. So basically, they do the prediction, and this is, for example, the response of each story they have. If they have multiple stories, it would be, let's say, if they have Q stories, it would be Q features. But what they are doing as they go from input parameter space to their output, they are doing some sort of downsampling, depending on the window size they are considering. But it was really successful in terms of capturing the response on the problems they have studied in that application. So we decided to build our model on top of this model, but we made some changes here. One thing that we did, we really want to consider the uncertainty in the input excitation and also other time invariant variables we have, like the soul velocity or the angle of incidence and so. So that is another set of scalar variables we have. So we decided to have that one added to our input layer. And in addition to that, we want to avoid that downsampling that we do as we go from input to output. And in order to do that, we use the functional API that is available for Keras, that you are more flexible to design your architecture for your LSTM model. So with this, we call it for now LSTM-W, and then we wanted to see how it performs in predicting the response of dynamical systems. And we tested two systems for now, one discrete and the other one continuous. So let's take a look at the, before that, we also, for all the results that I'm going to show now, we had 10 earthquake records that we test predictive capability of our models using them. And none of them have been used for training our surrogate model. So the very first example we studied was a multi-degree of freedom system. So here is how we are defining some set of uncertainty in our input parameter space. For example, I have some uniform distribution for my first spring stiffness, and some distribution for my modal damping, and also other stiffness coefficients. And we are interested to, and also we want to have some randomness in terms of the input excitation. So we tried different excitations to see which one are good in predicting the response to earthquakes. So first we went with harmonic and Richter wavelet. We tried to define some distribution for the frequency or the amplitude, and they were successful in predicting the response to harmonic excitation and Richter wavelet, but not for earthquake. And because of that, we decided to go with the white noise. However, what we did was just using 5 seconds of the white noise. And for example, the delta T could be 0.02. This is how we are training our model. And then we want to see how it performs if I have an earthquake as an input. And the duration could be completely different from 5 seconds. So this is the setup we have. And now let's see how our model is working. So these are now I have that 10 earthquake with different time series, time duration that we fed into the model, plus the randomness I have in my spring and dashboard coefficients. And this is the R² value, value we have at each degree of freedom. That all of them are relatively close to 1. And if we take a look at the results for any specific earthquake we use, you see that for all of them, we can predict the displacement of the degrees of freedom quite well. And we have done it for different durations. For example, here I'm using 60 seconds and the other one is 30 seconds. Although we have trained our model only for 5 seconds using Poisson. So that was one example for using multi-degree of freedom system. Now let's see how it works if I have my solar structure interaction problem. As a very first experiment, we considered the homogeneous half space. However, I assume my velocity in that domain has some distribution, log normal distribution that you see here. I also consider some variation in the angle of the incidence. We define some uniform distribution for that, changing from 0 to 30, and 30 is relatively close to the critical angle we can consider for this problem. And then I also wanted to have uncertainty in the time series itself. So again, I'm going to generate my database for training using white noise excitation and see how I can use it to predict under airspeed. So this is the setup I have. What are my quantities of interest? For now, we assume that, okay, we're interested to compute the displacement response at these 4 corners. Of course, we can add other quantities to the output layer as well. So we need to generate our database. For generating data, we did direct forward simulations using direct modeling approach. For all the modelings, we use the Seismic lab, which is an open source finite element solver suitable for solar structure interaction problems. And then in order to absorb the scattering waves, we use perfectly matched layers, and for modeling the incoming waves, we use the domain reduction method. So this is how we define our domain, and then we run it under different white noise excitations by having samples from these distributions and get our outputs as these quantities of interest here. Then we use that for training our model. So this is how the results look like when, again, I do prediction under the airspeed excitation using different durations, and you see that for all cases, the R² value is close to 1. That shows the goodness of performance for this model. And if we take a look at 2 of the airspeeds, so here is airspeed number 10, you see that we have done a very good prediction for the response at all 4 corners. And also we studied kind of an extreme case that, let's say we have the VS to be 50 meter per second and the angle is 0. So it is more or less, at these extreme points that we can have for this distribution. And even for that case, we have a good prediction in the response and capturing the response under the airspeed. So with this, so as I mentioned, one interest we have is, okay, how we can do the acceleration for these UQ tasks. So let's look at this problem. Now let's say that I have this model and I want to see how I can estimate the maximum racking or predict that under some uncertainty I have. So I have trained this model. Now let's say that I have a new airspeed and I want to compute the response, and from that compute the maximum racking in my buried structure. So the input motion is fixed, but I have some uncertainty for my velocity and also for my angle of incidence, and I want to compute the response. So I define different types of scenario. The first case is that let's use my direct modeling approach, and I do 100 samples from these 2 distributions and run the model only for 12 seconds and see what would be the computational cost for that. So for that, the runtime would be, for each simulation, it's about 342 seconds, and the whole thing would be this budget that I need in terms of the runtime. So the second scenario is, what if I do this finite element using 1,000 samples from those distributions, and what would be the budget I need, which is basically here. And the third scenario is, okay, let's see how much I need to train a model and then use that for prediction. For training the model, since I'm using the voice noise and only 5 seconds, so the duration I need for having the forward simulation would be 145 seconds, which is 42, because I'm not using the same airspeed excitation, and I only did sampling for 100 cases. So this is how the training size I decided to use. Training and validation basically. And then for training the model, the time it takes for that specific problem was about 160 seconds. Then after having this trained model, I want now to do lots of forward simulations. So now let's say that I'm going to use 1,000 samples from this distribution and do my predictions to see how my PDF will look like if I want to estimate the maximum vacuum. So if I do this, then let's see how the results will look like. And as you see here, for example, for this case, if I use that surrogate model, and if the cost for that is 1, then for the case that I do 1,000 simulation would be 23 times, and for 100 simulation, it would be 2.3 times. So these are the PDF for the racking displacement, the maximum racking displacement when I use that LSTM-W approach, or when I use 100 forward simulations for the airscope. And you see that, and I'm showing that the PDF for the left and right edge of that buried structures. So we see that there are some discrepancies, especially for the tail, and also we see some changes or discrepancies in this part. So it seems that therefore the 100 samples that I did, sampling that I did from, use under earthquake to predict that racking, maybe it wasn't really enough. What if I had 1,000 samples for my earthquake and then 1,000 sampling from my LSTM model? So here is how the distributions look like. So we converge to similar distributions when I increase the number of the samplings, but with the LSTM-W, I can capture the same distribution at this fraction of the cost that I have here. So with this, we also have checked how the model would work if now I introduce some uncertainty in terms of the velocity profile. So if I have a heterogeneous VS, I define some, let's say, a variation for the VS using this functional form, and each of these parameters can change based on these distributions. And again, we test that, we train the model and then test that under those earthquake excitations. And here is how the R-squared looks like, which again shows a good performance. And here is the case when we take a look at each of these predictions. So for the first case now, we have just randomly selected one profile with this earthquake, and this is how the results look like for 40 seconds. And this is another example that we chose another set of random variables and computed the response. So with this, so this is what we have done so far, and the results are showing, seems to be promising, at least for the linear problems we have studied so far, and we could train the model for a short duration and do prediction for a long time. And also we could add scalar or time invariant variables in our input parameter space beside our time series. But we need to see how it works when we have nonlinear problems. Our results are showing for most that it is successful, but we need to check it for the SSI problem as well. So this is one thing that we want to study as a next step. So what happens if I have even more complex soil profiles and soil and structure nonlinearity? The other thing that we want to see is what would be the gain we have if we want to use such a surrogate model in performance-based engineering applications to derive the fragility functions. And at the end, also, we're very interested to see how we can use this surrogate models in the multi-fidelity setting. That what we want to see is that probably as our problem becomes more and more complex, the R-squared value or performance of these surrogate models can decrease. And then the question is that if I can have this model as part of the case that I run a bunch of low fidelity models or my surrogate, and beside that, decide on a number of high fidelity models to run at the same time, how that will affect the results and how I can reduce the bias in my predictions when I'm using that. So here is an example of using this framework for a multi-degree of freedom system, that you see that for each budget that I have, let's say that I have a 10-second budget. And if I use the high fidelity model, I need to go with lower number of the samples I have, right? So let's say that I can only run 10 high fidelity simulation, and then I can do some MC estimation of the quantity of interest for this case. And this is the mean square error I have for, let's say, 10 seconds. But in the multi-fidelity multi-fidelity setting, I can use the same runtime of 10 seconds to run maybe 100 low fidelity model and 2 high fidelity model. And with that, I would have probably a better estimation because now I brought that high fidelity model in the loop of my UQ task. And this is, as I said, this is the result we have for a multi-degree freedom system case, and we want to expand it for our SSI problem and see how the result will look like and what is the gain we will have. And with this, I'm done with this presentation, and thank you for your attention.
Maybe one quick question.
Could you talk to us about your superstructure? So the structure part of your soil structure interaction and how that's affecting your results because you looked at your soil.
So those results that I showed were on the structure. It was four values that I had at 4 corners of the braided structure, but it was a continuum concrete model, and we didn't consider any nonlinearity. So that is something else we need to consider.
Great. Thank you so much.
Thank you.